Okay, in this video we're going to prove two theorems about splitting fields. So suppose you have a subfield of C, f is a non-constant polynomial over K, then there exists a unique splitting field, sigma for f over K, and our splitting fields, remember, are subfields of C, so it is in fact unique. It's like unique equals, not unique up to isomorphism, unique equals. Moreover, the degree of sigma over K is finite. Right? Let's set our splitting field to be K adjoin the roots of f. And this is what we need to have access to all of the roots, is this guy, and f splits here, over sigma. And if sigma prime is contained in sigma, also has access to the roots, then sigma 1, I'm sorry, K is contained in sigma prime contained in sigma. Sigma 1 through sigma n are in sigma prime, and K is a subset of sigma prime. So, by definition of adjoining roots to K, we have a field, sigma prime, that has all the zeros and has K. So by the smallest condition, when we defined adjoining, sigma is actually also contained in sigma prime, and so sigma equals sigma prime. Okay, so that's that first part. It's a formalization of what I said in the previous video. For the degree condition, the degree of sigma over K is inductively computed as the degree of sigma over K adjoins sigma 1 through sigma n minus 1, and then all the way down to K adjoins sigma 1, K. So you can just keep adding in a root after a root after a root after a root. Each time we do this, well, each time we add, let's be specific, we add a 0, the degree is the degree of the minimal polynomial, which is finite. And so each one of these degrees that makes up this product is finite. So sigma, the degree of sigma over K, is a finite product of finite numbers. So finite. You could do an induction argument too there if you wanted, whatever. But the degree actually is finite. So splitting fields have finite degree over the base field, which makes sense. We're only adding in finitely many roots of a polynomial, so that makes sense. We're going to prove another lemma. So suppose that iota from K to K prime is an isomorphism of subfields of C. Let f be a non-constant polynomial, well, I guess even non-zero, whatever. The distinction is not important. Polynomial over K with splitting field sigma. Let's let L be an extension of K prime such that iota of f splits over L. Then there exists a monomorphism J from sigma to L such that J restricted to K is iota. Equivalently, the diagram commutes. So we have K going to K prime, isomorphism via iota. K is extended by sigma, where we just add in the roots of our polynomial f. And K prime is extended by L. And we have some polynomial here over K. We change the coefficients, so now they're K prime coefficients. And we know that iota of f, once we've changed the coefficients to K prime coefficients, we know that it splits over L. And sigma knows about the coefficients. Sorry, sigma is a splitting field with f, so the original coefficients. And it's saying, this theorem is saying, that we can actually extend that isomorphism to a monomorphism, so inclusion, and that's J. And we can do it in such a way that it respects the map iota if we're plugging in guys from the base field. Okay. All right, so let's prove this theorem, this lemma. It'll be a helpful lemma. Okay, so we're going to construct J by induction on the degree of f. All right, so we need to understand how to take elements of the splitting field, which is just K adjoined roots, and send them on over. All right, so let's do that. We can view f as a polynomial over sigma, because it's an extension of K where f splits, in which case f is K times t minus sigma 1 all the way up to t minus sigma n. Some leading coefficient, which is in the base field, and then we have a product of the linear guys that corresponds to the roots. So where here, sigma 1 through sigma n are in capital sigma. Great. So the minimal polynomial of the first guy over K is irreducible. Is an irreducible factor of f, rather. F need not be irreducible, is the thing. Like the t squared plus 1, t squared minus 5 example we did in one of the earlier videos. And since, therefore, m divides f, the same is true after applying iota. The polynomial iota of m, where we just change the K prime coefficients, that's all, divides iota of f. Great. And iota of f splits over L. That was one of our conditions. L is a field over which the guy splits. So, over L, we can write iota of m as t minus alpha 1 all the way up to t minus alpha r, because it splits completely, and the minimal polynomial is monic, so there's no leading coefficient. Iota was an isomorphism, though, and iota of m was irreducible over k, and so iota of m is irreducible over k prime. So it is the minimal polynomial of each one of these alphas. And I'm just going to single one out. It's the minimal polynomial of alpha 1 over k prime. All right, so we proved a while back that when you have an isomorphism of fields and you add in, and you have an irreducible polynomial, and you take a root of one of those polynomials in the one field, and then a root of the image of that polynomial under the isomorphism, in this case iota, then those guys obtained by adding in just one of the zeros are isomorphic. So there exists an isomorphism, J1 from K of sigma 1 to K prime of alpha 1. Right? So K and K prime are isomorphic. So I'm going to get an isomorphism of the corresponding simple extensions because the minimal polynomials match up. And what this J1 does is it covers iota, so it agrees with iota on K, and J1 of sigma 1 gets sent to alpha 1. The roots get sent to each other. Great. But sigma is a splitting field. Then over K of sigma 1 of G, which is F over T minus sigma 1. So it's a polynomial where this splits. And by induction, we can then extend, and then K prime of alpha 1, that of course includes into L. So J1 is sort of our first step where we add one root. And then by induction, we can then extend this to a monomorphism, sigma to L, because G has degree 1 less than F. And that's the end of that. So sorry that lemma was a little bit long. We'll apply it here in a second.